Welcome to this presentation on accessing and plotting the data from the Geostationary Lightning Mappers, or GLMs. My name is Joseph Patton. I'm a faculty researcher at the University of Maryland, and I'm here to help you better understand how to use the GLM data and how to plot it as well. This first part of this presentation is going to discuss how to access real-time and archived GLM imagery and data files. One of the best real-time sources of GLM gridded products is the NOAA NESDIS Star Goes R viewer. This webpage will allow you to select different sections or sectors in the United States. We're going to start here today with the Florida Peninsula. Once you click there, there'll be an option for GLM FED, and you can click on the animation loop. And that animation loop will show you the GeoColor product, which is derived from the ABI, as well as GLM flashes with the color bar that's seen at the bottom. You can change the image that you're viewing at the slider at the bottom, and you can also download this animation as part of an animated GIF. And this will allow you to save the imagery to your computer and use it for any applications that you may want. One of the other really good resources for real-time GLM gridded products is the College of DuPage Meteorology website. At this satellite section, you can select product overlays, and then from there on the drop-down menu, you can select GOES derived products, and it'll show all the GLM gridded products, the flash density, minimum flash area, and total optical energy. If we select flash density, then our GLM flashes show up. And we can even select a sub-regional sector, so we can go back to the Florida Peninsula and get a similar image as before. And this is in a more familiar color scale that was shown on the previous presentation. And we can even change that product overlay within the GOES derived. We can change it to minimum flash area, and we can also change it to total optical energy. And in order to download this imagery, all we have to do is click the download button just below where we have the product overlays, and that will allow us to select the number of frames and the timing between the frames as well. An important distinction that I want to make here is the difference between the level 2 GLM products and the level 3 GLM products. For level 3, we're talking about the gridded products like flash extent density, minimum flash area, and total optical energy. But those archived data files are not necessarily very easy to acquire, and the level 2 data, which has just the flash characteristics from individual flashes from the GLM, are more readily available via NOAA. So the level 2 flash data includes the location, energy, and area of individual flashes, but it doesn't provide the aggregate flash characteristics like total flash counts, the spatial coverage, and the smallest flash from MFA, or the accumulated brightness that we see from TOE. The level 2 GLM data points each represent individual flashes and their characteristics, and the level 2 data also includes lightning events and groups, which, as you may recall, are amassed together to construct the GLM flashes. The best and most accessible archive source of GLM level 2 files, or LCFA files, which stands for Lightning Cluster Filter Algorithm, is going to be the Google Cloud bucket, which is operated by NOAA at that URL on this screen. And you can change the URL from at the end where it says GOES 16, you can change that to GOES 17 or GOES 18 to get the GOES West satellite perspective. So on this website, if you click that link, it's going to look like the image in the top right here. And it's going to be listing a whole lot of products from the different GOES satellite instruments. We want to scroll down to where it says GLM L2 LCFA and click there. And from there we can select the year and then the calendar day of the year out of 365 and then the hour. And once we do that, we'll get to these individual netcdf files or .nc files, which will contain the 20-second data from the GLM instrument. So each file is only going to be covering a span of 20 seconds, and each file contains the level 2 information on flash characteristics from the GLM. Each of these GLM level 2 LCFA files are created every 20 seconds, so that's 3 files per minute. The files are in the netcdf file format, which is a pretty common standard in earth science applications. These netcdf files can be opened fairly easily in Python or in MATLAB, whichever you prefer. And the next section here explores opening a level 2 GLM data file and plotting its contents. This second part of this presentation will go over how to open and plot the GLM level 2 LCFA data files. First, some information about the Jupyter Notebook itself. In order to run the notebook locally, you must start in the same directory where the Jupyter Notebook file and the GLM data file is located. And once you do that, you just have to type in Jupyter Notebook. And we're going to need the following modules, which are displayed at the bottom of the screen there. Those modules need to be installed in your local Python environment, just like Jupyter. Those modules are netcdf4, matplotlib, and cartopy. And make sure to have the right capitalization in netcdf4. In order to run our Jupyter Notebook locally, all we have to do is be in the right directory where our Jupyter Python notebook is located, as well as our data file. So if we run a quick ls command, we can see that our data file, the GLM level 2 LCFA data file, this is a netcdf file, is in here, as well as the Jupyter Notebook that we're going to be exploring today. So to start the Jupyter program, we just have to type Jupyter Notebook, and you have to make sure the Jupyter module is installed in this Python environment that you're running. So Jupyter Notebook, and hit enter. And this is going to open a separate window in a web browser, which will allow us to explore this data set further. Once we run the Jupyter Notebook command, it will open up this tab in a web browser. And in this tab, we can see that we have the Jupyter Notebook itself, plot LCFA flash counts, and it's also listing our data file, which we're going to be opening today. So to open up the Jupyter Notebook, just click on it, and it will open up in a separate tab. And from this separate tab, we can see our individual cells in which we have written some Python code in order to parse out this file. So the first thing we need to do is we need to import the right packages, and these packages should be installed on that same Python environment that you're running from the terminal where you enter the Jupyter Notebook command. In this case, we only need 3 Python packages. That's going to be netcdf4 to open up our netcdf file, and then matplotlib and cartopy in order to plot our data on a useful plot and map. So if we run this, all you have to do is click this run with a play button here in the top center, and it's importing our features. Next, we want to import our data set into this code, so we can use the nc. Remember, we imported netcdf4 as nc, this nc command with dataset, and we give it the name of the data file that we're trying to import. Remember that these LCFA data files are only 20 seconds long. So we're opening it in read mode, which is what this R in quotes means. So once we run that, we've imported our data set. And the third thing that we're going to do here in the third cell is we're just going to print out the data set information itself, which we can do by simply typing the name that we've given, G16GLM or Go16GLM, to this data set. Click Run. And this will show us some useful information, including where the data set is from, what the file format is, a summary of the data set itself, so it contains events, groups, and flashes from the GLM. And recall that events and groups are amassed into flashes so that we can have this lightning product from the GLM. It tells us the spatial resolution, which is 8 kilometers at nadir. So that's 8 kilometers at the center of the field of view of the instrument. And that stretches out to about 12 or 14 kilometers at the edge of the field of view of the instrument. It also tells us the time coverage start, which in this case for our data file is going to be April 17th. And it tells us the time coverage end as well, which is 20 seconds later. So it gives us a list of variables and the dimensions on which they are dependent. And we can also get a list of variables by doing this variables.keys function. So if we take the name of our dataset, g16glm.variables.keys, parentheses, and run that, we get a dictionary of all the different variable names that are associated with this particular data file. The two that are going to be most important for us in this exercise are flash lat and flash lon, which are the latitudes and longitudes of each particular flash that are observed by the GLM during this 20-second window. So in order to examine exactly what one of those variables looks like, we can do g16glm.variables, and then in brackets here, the name of the variables in quotes. So the flash lat is our latitude coordinate in degrees north on the y-axis of our flashes, and it's dependent upon the number of flashes. So however many number of flashes there are, that's how many entries we have in the flash latitude variable. So we want these flash latitudes and flash longitudes. That's going to be able to help us plot the flashes and get the data to plot on the map that we want to show in a density product. So if we run this next cell here, we will import the flash lat and flash lon variables from our data set as arrays into our program. Also, things that may be of interest are the flash area, so what the spatial coverage of the flash is, and the flash energy, so how much brightness is being observed from each individual flash. So we can import those as variables as well. And then this final thing we're going to import here is the start time, or time start. And we're getting that from one of the attributes, not one of the variables. So we have to do g16glm.getNCATTR to get the attribute from the netcdf file. And this attribute that we're going to be getting is called time coverage start. So we'll run that. And now, just to make sure that our time start looks correct, we can simply type the name of the variable and it will give us its contents. And in this case, that's April 17th on 2023 at 16:27Z and 40 seconds. So this next cell here, what we're going to be doing is we're going to be actually plotting the data. And the plot of the data has several steps, which we have to do all at once in order to be interpreted correctly by the Jupyter Notebook. But don't be daunted by this. Don't consider this too daunting, as these are all just separate parts of what would be a normal Python program when plotting data like this. So the first thing we have to do is we have to declare our figure. We can declare it using the module PLT. And PLT is how we imported matplotlib.pyplot earlier. So the PLT simply allows us to use this matplotlib.pyplot function in order to create some of the things we'll need for our plot. So we're going to declare a figure with this size 10 by 10 and this resolution of 100. And we're also going to set the coordinate reference system as a standard CRS, which is called plate carré. And this is going to be imported into our figure, and it's going to be the basis for how things are plotted near each other in a map style for our figure. On top of that, we want to bring in some identifying geographical information. So we can use Cartopy to easily add these features here. The first one we're going to be adding is coastlines, and we're going to be coloring the coastlines black and giving it a line width of 1.5. And the next features we're adding here are borders, so country borders. We're also going to be adding state borders. This is that admin1 states, provinces, lines bit. And you may get a warning about having to download a shapefile for this, but that's totally normal. And we're coloring the edges of them black. And we're also going to be adding a land feature, which is going to be light green, and adding an ocean feature, which is going to be cyan or light blue. So all of this will create a realistic looking map on which we can plot our data. The next thing we have to do is we have to set the extent of our data set that we're going to be plotting. So in this case, there's a fair amount of lightning along and off the coast of the Florida Peninsula. So we're setting our data set as going to be from 75 west to 85 west. That's negative 75 to negative 85. And then also from 20 degrees north to 35 degrees north. And that's going to be 20 and 35. So it's our far right coordinate, our far left coordinate, our bottom coordinate, and our top coordinate. And we're going to be using M is the name of our figure here. So we're using the set extent function to set the extent as that array that we've created. And you can change this array around in order to plot a different area. And then finally, what we can do here is we can actually plot our data itself. So we want to make a sort of pseudo-density plot of where the greater number of flashes are occurring. So this pyplot function called hexspin, what it does is it creates a grid of hexagons, and the data is confined. The data within each hexagon is then counted up and given as a total count of the number of flashes within that hexagon. So in this case, the data we're plotting with this hexagon function is flash lat and flash lon. This grid size here tells us how big the hexagons are going to be. The log bins tells us that it's going to be a log scale. And we're setting the color map as jet, which will have cooler colors as small numbers and warmer colors as larger numbers. And we can also set the minimum and maximum of our color map, Vmin as 1 and Vmax as 30. So this will display a color map ranging from 1 to 30, and anything over 30 is just going to be assigned this 30 value. And then finally, this Z order here of 10 just tells us that the data is going to be plotted on top. So it's not going to be obscured by any coastlines or any other borders or geographical features. This is going to be on top of everything. Finally, we want to give our figure a title, GLM L2 flash density, and this is where our time start variable comes in. We can put that time start straight into the title itself. And we're also going to be adding a color bar. So this color bar is going to be based on our data density, and it's going to be oriented horizontally. And we're also going to give it a label to explain the colors, and the colors are going to be directly related to the count of the number of lightning flashes within each hexagon. So we'll call it count of lightning flashes. Finally, to show the plot, we only have to do plot.show and then parentheses. So now we can run this cell, and it's going to create our figure. It's going to set the coordinate reference system. It's going to add these geographical features. It's going to set the extent. It's going to plot our hexagons of data and give it a title and a color bar. So let's run this. This may take a few seconds. And now, as a result, we have our plot. So at the top here, we have our title. And in the middle, we have a series of hexagons, which are colored depending on how many flashes are contained within each hexagon. So these darker blue colors are a small number of flashes, likely just one. And these warmer colors, these yellows, are where we have several more flashes showing up. And we have our color bar here at the bottom. So it's the count of lightning flashes. 1 would be this dark blue color. And we can see that the yellow colors are closer to almost 10 flashes, or maybe even a little bit more. So this gives us a rough idea of how to plot the LCFA data from the GLM Level 2 products. and we can create this density product which shows us where more flashes are occurring within a specific area. Finally, in summary, I want to reiterate that the GLM gridded products provide valuable insights into lightning activity and thunderstorm evolution. These gridded products are available as imagery in real time through multiple websites, including the NOAA NESDIS STAR viewer. And the GLM Level 2 data files, which are not gridded products but instead contain individual flash characteristics as points, those are readily available through the GOES-R Google Cloud bucket as data files. Python can be used to easily plot the GLM data files as well as other map features, which we've shown in this exercise. And finally, if you have any questions or comments, please feel free to email me at the email that's on screen, or see me in my office hours, which are going to be Monday, October 2nd, 2023, from 2 p.m. to 4 p.m. Eastern Time. Thank you very much for participating.